Good morning, students. Today we will discuss productive property of completely regular topological spaces. So in order to discuss this property, we require two lemmas. So firstly, let us discuss these lemmas one by one. So the first lemma is, let us consider a topological space X top and beta is the base for the topology top. Then the topological space X top is completely regular if and only if for each X belonging to the topological space X and A belonging to the base beta with X belonging to A, there exists a continuous function g from the topological space X into the closed interval 0, 1 such that under this function g, the image of the point X is 0 and the image of the complement of A, that is singleton 1. So first of all, let us take the topological space is completely regular and we prove this condition. Let us take X belonging to X, A belonging to base beta with X belonging to A. Now we prove that we have a continuous function g from X into the closed interval 0, 1 such that the image of element under that function is 0 and image of complement of the member of base, that is singleton 1. Now because A is belonging to the base beta and beta is a sub collection of the topology top. Therefore, we can say that A belongs to the topology. Now we can combine these two conditions. We have X belonging to A and A is a member of the topology top. A belongs to top. Now X belonging to A and A belongs to top. So we can say that A is neighborhood of the point X. Yesterday we have discussed the characterization of completely regular topological spaces in terms of neighborhood of a point. So we can use that characterization here. So using that characterization, because X is completely regular, so we have a continuous function g from the topological space X into the closed interval 0, 1 such that the image of point X under G is 0 and the image of complement of A is singleton 1. So this proves one of the parts of the lemma. Now we do the converse part. Conversely, we are to prove that the topological space X is completely regular. To prove completely regular, we will prove the same characterization which we discussed yesterday. To use, let us take X belonging to X and W is a neighborhood of point X. Now because W is neighborhood of X, so by definition of neighborhood there will exist a member G from the topology such that X belongs to G is contained in W. Now because beta is base for the topology, so by definition of base there will exist a member A belonging to the base such that X belongs to the existing member A that is contained in G. Now we can combine these two. We have X belongs to A is contained in G and G is contained in W. So from here we get A is contained in W. Now we can take complement on both sides. So we get complement of W is contained in the complement of A. Now we can use the given condition. So by given condition, we have a continuous function g from X into the closed interval 0, 1 such that the image of point X under G will be 0 and the image of X minus A, that is singleton 1. Now because X minus W is contained in X minus A, so the image of complement of W, that will also be singleton 1 because the image of complement of A is singleton 1. So we have proved the both conditions. image of point is 0 and image of complement of the neighborhood, that is singleton 1. So by the characterization of completely regular topological spaces, the space is completely regular. So this proves first of the lemma. Now we prove the lemma 2. In the second lemma, in the topological space X tau, we have alpha is the defining subbase for the topology tau, and we have to prove that X is completely regular if and only if for each X belonging to the topological space X with A belonging to subbase with X belonging to A, there exists the continuous function h from X into the closed interval 0, 1 such that image of the point X under existing function is 0 and image of complement of the member of subbase, that is singleton 1. So first of all, let us take the space is completely regular, and let us take for each X belonging to X, A belonging to alpha with X belonging to A. We prove that we have a continuous function h from X into closed interval 0, 1 such that these two conditions holds. Now, as we discussed in the first part, in the same way we can do here, because alpha is subbase for the topology and subbase is a sub collection of topology. So alpha is a sub collection of topology tau. Therefore, the member which is from alpha, that will also be in the topology tau. Now here we have taken X belonging to X, A belonging to alpha with X belonging to A. We can combine these two. So we can say that A belonging to alpha is contained in tau. Therefore, we can say that A belongs to the topology tau. And also because X belongs to A, so we can say that A is the neighborhood of the point X. Now, because the topological space is completely regular, so we can use the characterization of completely regular spaces in terms of neighborhoods. So by that characterization, there will exist a continuous function h from topological space X into the closed interval 0, 1 such that image of the point X under H is 0 and image of complement of A, that is singleton 1. So this proves one of the parts. Now conversely, we are to prove that the topological space X tau is completely regular. In order to prove the space is completely regular, we will use the above lemma. In order to use that lemma, let us take beta is the base for the topology, and let us take a point X belonging to the topological space X, H belonging to the base beta with X belonging to H. We are to prove that there exists a continuous function h from X into the closed interval 0, 1 such that image of the point is 0 and image of complement of H is singleton 1. Now, because H belongs to beta, by definition beta is base for the topology and the members of base, they are finite intersections of members of subbase. So we can write H as the finite intersections of the members taken from alpha. Here alpha is subbase for the topology tau. So we can write H is equal to intersection of AK, where K varies from 1 to N, and these AK, these are the members of the subbase. Now because X belongs to H, it means X belongs to intersection of these AK. Here K varies from 1 to N. So by definition of intersection, it means X belongs to each AK for every K. Here K varies from 1 to N. Now, because X is belonging to AK are members of the subbase, so we can use the given condition. So by given condition, we have a continuous function HK from X into the closed interval 0, 1 such that under this function HK, the image of the point X is 0 and image of complement of A, that is 1. This is true for, this is for the complement of AK. So that will be singleton 1. This is true for every k varying from 1 to n. Now we are having the functions h1, h2, h3 up to hn. Let us take h be the supremum of all these hk, because each function hk, that is continuous function, so we can say that h is also continuous. Now under this function hk, the image of point x, that is 0 for every k. Therefore we can say that will be true for the supremum also. So we can say that image of point x under function h, that is 0. Now let us find the image of the complement of h. Let us take y belongs to the complement of h. It means y does not belong to h. Y does not belong to h, it means y does not belong to intersection of ak's, where k vary from 1 to n. Because y does not belong to intersection, it means there will exist some member out of a1, a2, a3 up to an, such that y does not belong to that member. So let us take aj is a member from out of a1, a2, a3 up to an, such that y does not belong to aj. Now y does not belong to aj, it means y belongs to complement of aj. And if y belongs to complement of aj, its image under the function hj, that is 1. So the supremum will also be 1. So we can say that image of y under the function h, that is 1. And y is arbitrary element of complement of h. So we can say that image of complement of h under the function h, that is singleton 1. So we have proved the topological space is completely regular. Now let us come to the proof of the main theorem, productive property of completely regular topological spaces. It means product of completely regular topological spaces is completely regular. So let us take a collection of completely regular topological spaces. This collection is given by the collection of the members xi with topology tau I. Here I belongs to the index set. Let us take x is the product of these xi's and tau pi, this is the product topology on the set x. Let us take alpha pi is the defining subbase and beta pi is the defining base for the product topology on x. In order to prove the topological space is completely regular, we will use the lemma 2, which we proved already. So we proved that for each x belonging to x and a belonging to the subbase alpha pi with x belonging to a, there exists a continuous function from x into the closed interval 0, 1, such that under the existing function image of point x is 0 and image of complement of the member a, that is singleton 1. We will prove this. So let us take an element x belonging to x and a belonging to the defining subbase of topology tau with x belonging to a. Now because a belongs to defining subbase, so by definition of defining subbase, a will be of the form of very special products. It means a will be of the form product of ai, where ai is equal to xi for all except one I, and for that I, ai belongs to the topology tau I. Now because x belongs to a, so and a is of the form of very special products, so by definition x is of the form of product of xi, where these xi belongs to ai for every I belonging to index set. Now these ai's, these are open in the topological spaces xi, and xi is completely regular. So by definition of completely regular, there will exist a continuous function gi from the topological space xi into the closed interval 0, 1, such that image of point xi under gi, that will be 0, and the image of complement of ai, that will be singleton 1. Now pi is ith projection map from X into Xi, and Gi is a mapping from Xi into the closed interval 0, 1. So their composition Gi of Pi, that will be a mapping from X into the closed interval 0, 1, and this mapping will be continuous also because that is a composition of two continuous mappings. So this is continuous. Now let us find image of the point X under this mapping. By definition of composition, this can further be written as Gi of Pix. Now by definition of ith projection map, Pi of X, that is the ith coordinate of the topological space Xi. Ith coordinate of the point X means Xi. So this becomes Gi of Xi. Now from here Gi of Xi, that is 0. So this is 0. Now let us find the image of complement of A. Let us take an arbitrary element from complement of A. Now y will be of the form of product of yi's, where this yi's belongs to xi. Let us find the image of this y under this composite mapping. By definition of composition, this is Gi of Pi of y. Now by definition of ith projection, Pi of y means the ith coordinate of y. Ith coordinate of y will be yi. So this will become Gi of yi. Now because y does not belong to A, it means y does not belong to product of ai's. It means one of the coordinates of yi will not belong to ai for some I belonging to the index set. Now yi belongs to the complement of ai. It means yi belongs to xi minus ai. So the image of yi under the mapping Gi, that will be 1. Therefore Gi of Pi of y is equal to Gi of yi, that is 1 from here. And this was arbitrary element of complement of A. So we can say that image of complement of A under this composite mapping, that is singleton 1. So by definition we can say that the topological space X with the topology top I, that is completely regular topological space. So this proves that product of completely regular topological spaces is completely regular. So this completes the productive property of completely regular topological spaces.